I want to let y'all know about, I think it's problem or set 4.3 in the homework, that I overestimated how flexible Edfinity was going to be. So has anyone else had problems with this? I know one person talked to me about some of the questions here. So this is due tonight. So just to kind of recap, your question one probably doesn't look like this because they randomize them pretty well, but so I want to find a basis for the subspace spanned by these vectors. The way that I kind of went through this is, let me just ask you, what do you remember about the way we went about this? So we parameterized it and we found a basis. I didn't pay attention to the way this was programmed, but this is pretty rigid. So one thing we've talked about is that there is no such thing as a unique basis. If you have a subspace, there's an infinite number of bases or bases that will span them, and they'll be linearly independent. So let me give you an example here of what they're looking for. Let's not go through this by hand, but can someone reduce this for me? Who's got a calculator on who could do it quickly? Or who wants to fire up Desmos? Unsolved is 1 negative 300 1 negative 300 0010 0001 and then 0000, right? Okay. So the way that we went through these when we were covering this section is basically you can parameterize. I mean, the second and third row basically tell you that x3 and x4 are those are lead variables, right? X1 is a lead variable, x2 is a free variable. We could parameterize from here and make a basis, and that basis would be correct. Unfortunately, Edfinity is only looking for one thing. The thing that Edfinity is looking for is where the pivots are. So the pivots are in column 1, column 3, column 4. So the basis, as far as Edfinity is concerned, is the vectors that those pivots correspond to. So vector 1, vector 3, vector 4. So that is a basis. It's also the only one Infinity wants. So I just wanted to give you a heads up that I promise the way I've taught you is totally valid, but I didn't code Infinity. So it's just very, very rigid. So I didn't want you to bump your heads against that for longer than you needed to. Any questions on what it's looking for? Okay. So heads up on that. I pushed the due date out today just to give you a chance to address that. All right. So let's get rid of all my drawings. All right. Syllabus says the next test is going to be a week from today. I'm 90% sure that's actually going to happen. So it'll cover essentially chapters 4 and 5. Just like the first test, we'll do it in here during class time. I also put in the grades for the first tests. I apologize for how long it took. Yes, last week I had a lot going on. I normally will try to turn the test around within 24 hours. So that'll be the norm from now on. I can show you your test if you want to come by and look at it. I'm still waiting on one person to take it, so I can't hand them out yet. But once everybody takes it, I can give them to you. But if you want to talk about it in the meantime, let's do it. Any questions about where we're headed? Okay. I know it goes quick. I think we're about halfway done. So let's get back into bases here. So a few days ago, we were talking about this idea of coordinates. So again, bases are not unique. Like these three vectors here, 0, 5, 4, -3, -5, 1, 1, 5, 0, those span a subspace. I don't really know what that subspace looks like, but they span some subspace. There's an infinite number of other bases we could write that span the same subspace and are also linearly independent. So the thing we closed on Thursday was, if I give you a basis, we're finding these coordinates. So this thing that I boxed in here, what does this represent about what we asked?
Those are the coordinates.
So yeah, what I'm asking is like, what does that mean? I just want to make sure we're all on the same page again.
Multiply that set of vectors, and then you'll get the 6 times 7.
Okay, so how many of this first vector do I need? -2, -1, and 3. So basically, the coordinates tell you exactly what linear combination makes the target vector. In this case, that's 6, 10, 7. So that's just kind of wanted to refresh that. So let's do this now. Instead of taking a vector that's, given to you kind of plainly, let's talk about how to go from one basis to another. So I have this vector u, but this vector u isn't purely 2, -1, 4. This is with respect to this basis right here that I'll call B. So I know that some vector has these coordinates with respect to this first basis. Now I want to find the coordinates of that same vector with respect to this thing. So a little bit different than what we were doing last time, but any ideas off the bat how we get started?
Multiplication.
Yeah, what do you want to multiply?
E and 2, -1, 4.
Right, so what will that give us? If we multiply B times U, first of all, what order of a thing, what order of a matrix will it give us? Should be a 3 by 1, so it should be another column vector. And if I do this multiplication, what do I get? -2 plus 3 plus 12. 13. 6 minus 10 minus 48. Minus 52. Stop me if you disagree. 4 minus 6 minus 28. I believe that's what that multiplication gives. Okay, so multiplied. So we have this basis B, and we were given this vector U, multiplied them together, and I got this new column vector. What does this column vector represent? Well, the coordinates to B were, I believe, U. So one, I don't know, I hope I talked about this a little bit, but I talked about something last week called the standard basis. If not, then I'll go ahead and define that now. Basically, the standard basis for like any, in this case, we care about three-dimensional things, right? The standard basis for R3 would look like this. It'd be the span of, informally speaking, it's the 3 most logical vectors you would want for R3. What would those be? One. Right. So you'll hear it called the standard basis or the canonical basis, the one that basically whatever vector 1 has a 1 in its first position, vector 2 has a 1 in its second position, and so on. I believe this 13, -52, -30, these are the coordinates in the standard basis. So like if you were to look at this in the most intuitive way, probably, those are the coordinates you get. Are we done answering the question? What do we got to do now? Okay, so if I take this other matrix, this other 3 by 3, I go 1, 0, 2, 0, -1, -3, -1, -1, -6. And you want to multiply that by these coordinates in the standard basis. How do we feel about that?
One would be like dash dot result we get instead of like the -13.
I think so. This is very close, but I think what we really want is, here's the modification I'll make. Because what I think we're really after is this. I called this matrix B, I'll call this one C. Basically what I want is this. I want C times X equals 13, -52, -30. So I started with some coordinates in the coordinates with respect to basis B. Then we translated that to the coordinates, the standard coordinates. Now we want to know, like, all right, this new basis C, what are the coordinates with respect to this basis of 13, -52, -30? Is this the thing we've done before, the thing that I've written down? Basically, this is like I think every other example we've done in this section has been of this form. So where do we go from here?
In row 1 plus row 3 over.
Right, so we're going to do some elimination. We'll figure out later what kind of elimination we want to do. Maybe we'll stop early. So 1, 0, 2, 13. All right, row 1 plus row 3 is 0, -1, -4, -17. Good, got it. First column done. Now what? Do you mean row? Okay. We're not allowed to do things with columns. So row 2 minus row 3? Back to row 3? Okay. So 1, 0, 2, 13. Zero, 0, 1, -35. All right, now what would you like to do?
5 out.
All right, let's scale that. Done. Negative row 2 to row 2. Now what? Do we have to keep eliminating? If you want, we can bail out of it. Because what do I know?
C.
So we know that x3 is equal to -35. And from that, can we get x2? Right, so x2 should be equal to 52 minus 3 times -35. Is that 53? I think 3 times 35 is 105. No, I'm way off. 157. Okay. And then x1 is equal to 13 minus 2 times -35. 70 plus 13 is 83. So I believe that is our translated set of coordinates. Unless I did something wrong, which is absolutely possible. Questions here? So we put one extra wrinkle on this. to get from one set of coordinates to a different one. So this was very, very specialized, very specific to this one vector I had. So let's try to generalize this. So I have coordinates in one basis. So now I want to, or maybe I just have two bases. And I want to get from basis, let's say A to B. I want to get from basis A to basis B. And let's say the generic vector that I'm going to deal with is B. If I know that V are the coordinates of some vector with respect to A, let's just kind of think about what's the way we'll walk through this to get from one basis to another. Yeah, what do we do first? Almost. I'm going to be nitpicky because I have to be. A times B. Because they are very different in the things we're talking about. What did A times V equal? We're trying to get to some other basis, right? It equals B times, I don't know, W? Some other vector, right? So basically what we're trying to do is to figure out what is something I can multiply by V just to get to W? Or in other words, can we just isolate W here? Basically, I want to know how to, in general, how can I write W as a product of other things I already have without having to worry what V actually is? Go ahead. Yeah, because the way I'm writing this, I don't care what V and W are. Like basically, I'm trying to like write like a recipe for how to translate from one basis to another. Or more accurately, how to translate the coordinates in one basis to the coordinates in another.
Inverse B times A.
Inverse B. So if I do inverse B, multiply that from the left on both sides, what do I get? I get B inverse A V equals W. So this thing right here, this B inverse A, this is what's called a change of basis matrix. So we didn't really do this directly because we used the V as kind of like this intermediary, but we don't need to do that in general. If we have a basis we know we're going to translate from and a basis we know we're going to translate to, we can figure out how to translate between them by making this multiplication. Questions on the rationale there before I make us do one? Are these the same vectors I just gave us? I think so. So basically, I want to find that change of basis matrix from, A, this is like the source, and B is the destination. So if that's true, what's the calculation I'm going to make?
Inverse B times A.
Was it inverse B times A? B inverse A? Okay. Can we invert B? Could we do it by hand if we really, really wanted to? Would anybody be offended if we didn't? All right. Well, then I'm going to write this thing down to show that that's what we're actually doing. But if somebody wants to fire off the inverse, Anybody had it yet? All right, cool. Does everyone know how to do this in their calculator? Just in case a test happens next week where you're allowed to use a calculator. Okay. If you don't have a TI 80 something, I think any TI calculator, any graphic calculator will do it. I'm pretty sure the Casios will too. I just don't know enough about them to be of too much help. Okay, go for it. Inverse, yeah, was that just the inverse of B? Oh no. Okay. You did. Ooh. I'll corroborate. It's the only time I've ever heard anybody cheer for this thing. Go ahead. Is all the 11s? So I mean, in general, I think so let me just make sure that we have the right stuff before I give a quick crash course on how to. That's weird. Okay. Okay. So if this is to be believed, and the only reason it'd be wrong is if I type something in wrong. So weird that it goes to black when I'm not even a slideshow. Right there, at the bottom. Okay. So we have the right B, 1, 0, 2, 0, negative 1, negative 3, negative 1. Okay. So the inverse should be 3, negative 2, 2, 3, negative 4, 3, negative 1, 1, negative 1. And then the final product is whatever this thing said. Negative 5, negative 17, 19, negative 9, negative 31, 36, 2, 7, negative 8. So this right here is our change of basis matrix, which means if we would go back to our last example, so if we multiplied that matrix by this vector u, what should we have come up with? So this vector u is what? What does this represent? Yeah, so when we multiplied b times u, we got something in the standard basis, right? But what if instead of multiplying b times u, we multiplied this thing times the thing that I boxed in times u? What would that have given us? It actually goes further than that. It does not it goes further than C. It would give us this. So that's what I wanted to highlight is the change of basis matrix. So basically, let's just revisit what we did here. So I gave names here. I gave names to B, U, C, and then I didn't call this thing anything. I'll call this W, just to be consistent. So first thing we did was I multiplied B times U, and that gave us something in the standard basis, right? But what we really wanted in the end was I wanted to know what the coordinates of W would be with respect to basis C. And the way we got there was we left multiplying both sides by C inverse. So C inverse BU equals W. C inverse B is basically the thing that I just did on MATLAB. So the black matrix that's boxed in red. Which means basically we condensed a whole bunch of the operations we did here. So C inverse B is actually the thing we just found. And what that new matrix essentially does is takes any vector U that's with respect to basis B and translates it to some new vector W that's with respect to basis B. I'm going to stop there and take whatever questions you have. Like the example 3 here, we did this kind of like in really like a long sequence of slow steps, and then in example 4, basically condense this all into one thing. So I want to make sure everyone's comfortable with the fact that they're doing the same thing.
That's the next slide.
Yeah, for sure. The next example slide or this one?
Thank you.
Cool. Just B is. Oh, you know what? Let me change the names. Because what I was calling the source basis B and the destination basis C. So now everything should be consistent. But in here, there is no V. Because what I'm trying to do with this example is, regardless of what the vector is I'm going to translate, I want a matrix that will translate anything. So if B translates some vector U into CV, where B and C are both bases, then I can write this new matrix C inverse B, which takes any vector you want that's written in basis U and turns it into something written in basis C. But with respect to the standard basis, U and V would be the same thing. The only reason they have different numbers is because I'm giving you linear combinations with different building blocks. What else? I don't want to rush over this. Go ahead.
So, box, you have the box there, like the B inverse of A. Where does like the U come from, right?
So on this slide, there is no such thing as U and V.
Oh.
Because this thing right here is basically, this is a general, this will translate any vector you want. In example 3, I threw a vector at you so we could kind of build it up and see how it works. But in this one here, let me go back to example 3. The first thing we did is take vector U and translate it into a vector that looks like this. Actually, this is not W. This vector right here is standard. So this is what the coordinates would be if you had the standard basis. And then we use that as like this intermediate step to get to this thing. But in example 4, this matrix never deals with the standard basis. It goes directly from it goes directly between the bases you care about without going to that comfortable standard basis middle step.
Will it be important to know how to do both, or do we just have to?
No, I mean this is the goal here. Would it make you feel better if I proved to you this does what I told you it does? Since we had a rare happiness that was triggered by MATLAB, I'm gonna go back to it. So what is the change of basis vector is this? Okay, I still have it stored in answer. So ants times, what's my V? 2, -1, 4. Does that look familiar? Is that where we should have gotten to? Okay. So now instead of making the 3 different calculations to get there, the change of basis vector basically bakes in all those like simpler translations, not simpler, but intermediate translations. How are we doing? All right, putting this section to bed. All right, 4-5. Question?
How do we do the inverse?
Oh, that's a really good. Thank you. I did say I was gonna do that. Do I have any slides on here I can? All right. I believe that if you turn on a TI, and I'm sorry about Casio owners, I can find some YouTube videos if you want to just, I'm so inexperienced with Casio. But I believe on a TI calculator, you have like these 5 buttons across the top. Someone correct me if I'm wrong, I'm going off memory. And I think one of these says math on it. Am I right so far?
It's only, for me, it's like the first column, the fourth button, first column.
Okay, so math is on the first button here?
In that column, yeah, it's not like in that exact spot.
Okay, so one of these buttons has a math menu. Then underneath that, is there a menu that says MATRX? And then I think there are 3 options: list, edit. What's the other one? Yeah, the last one's math. Okay. So when you want to, if you want to invert a matrix, first thing you have to do is to make it. So press this edit button, and the first thing it will tell you to do is to define the order. So you'll set the number of rows and columns. So set the number of rows and columns. Then when you do that, you'll just kind of go entry by entry and type in all your entries. And then once you have that with all of your, basically any matrices you want to operate on, then under list, that's where you'll start calling them. I don't actually know if you can do like the alphabet keys and it'll work. I don't think it does. So let's say you have matrices A, B, and C. And what you really care about is doing B inverse A. Then the buttons you would hit, I believe, are list, then B, and then that'll dump you out to like your main command screen. And then you would do raise to the -1, which I believe will interpret the way you want. And then you have to go to list again, A, enter, and then that should spit out the actual product you want. I don't know if the TI does determinants and things like that. Does it? Cool. If it does, then I assume they're also underneath this same list of things.
Underneath.
It's under what? It's under math? Okay.
Yeah, it's like the first.
Oh, okay. Oh, okay. So yeah, get comfortable with it. Just again, I believe strongly you can do all these things by hand. Can you do them all by hand in 70 minutes? Can you do them reliably by hand? Make sure you know how to check your work. The good news is Texas Instruments has been making these calculators for 40 years. There's so many videos. If you have trouble finding some, I'll post them. And I'm sure the same is true for Casio. But yeah, let me know if you have any trouble and I'll point you in the right direction. How are we doing? Okay. So that was 4-4. Let's go to 4-5. And let's talk about a few different subspaces that all bases have. So these ideas of a row space, a column space, and a null space. So what are those things? Let's talk about which each one of those things are. So every matrix has these three subspaces. So there's a null space, which is basically all the vectors that if you were to multiply that matrix by that vector, you would get 0. So every matrix has at least one thing in its null space. What's one vector that I can multiply by a matrix and get 0? The 0 vector is always inside the null space of a matrix. In some cases, it might be the only thing that's there, but it's always there. But there could be more. So that's what a null space is. The row space, if you were to take the rows of a matrix, treat them as column vectors, whatever the span of those things is, that's called the row space. Column space is a very similar idea. Take the columns, let them span a subspace. That's called the column space. So really briefly, that's what these three things are. Let's talk about how to find them. Have we found any of these before? Does the null space sound familiar? Whether or not you realize that we've done very similar things, what about the column space? Let's refresh. Let's go back a few class periods. What does the span mean? If I talk about a few vectors, what's their span? I heard mumbling. What'd you mumble? Say it louder. That's if the span is. Oh no, that's. So it's linearly. What's linearly independent here? The vectors in A. They might be, but they don't have to be. So let's say we have a vector with a bunch of columns in it. The span of all those vectors, these are the linear combinations. Basically, if I were to take those columns, multiply them by whatever real numbers I choose, not linear columns, linear combinations. If I multiply all those columns by whatever real numbers I choose, then add all those things together, all the different combinations I can make, that's the span. If the matrix they come from is linearly independent, then that span is, or then those vectors are also a basis. But let's talk about how to find some of these things. So let's talk about the null space here. So as a reminder, I want to find basically all the vectors v that look like this. A times v will equal the 0 vector. What's the order of A? 3 by 5, which means the order of V is what? Always one. So vectors are always, by definition, a one column. And that equals a what? The zero vector of how many entries? 3. So I'm looking for all the vectors v that when I multiply a on the left, I'll get 0, 0, 0. When we talk about 0, 0, 0 is certainly in there, but maybe we'll find more. So how would we go about finding that? Okay. So, I mean, I'm not going to rewrite that matrix, but so we're going to just eliminate this, or we're going to augment it with something, or we're just going to eliminate this? Okay. If we augment this with 0, 0, 0, what is going to happen every time I do an operation on this 0, 0, 0 column? Nothing. So we really can we can just operate on this matrix. But so if we're going to do Gaussian elimination, so we're going to try to get this into row echelon form or reduced row echelon form. I was going to ask you what that would give us, but let's just start doing it. Maybe that'll jog your memories when we start getting into this a little bit. So when I start doing elimination, what's a good place to start? Get a 1 in the top left. How can we do that? All right, 1/2 of row 1 to row 1. 1, -3/2, 6, -7/2, -8. -5. All right, while I'm writing, is there anything else? Anybody else have an idea? Okay, negative row 2 plus row 3, back to row 2. Okay, I gotta do those one at a time, so we'll do that next. All right, negative row 2 plus row 3. 0, 7, 6. Yeah, what am I doing? 6, -24, 18. Oh, that's not going to work out that easily, is it? Oh, that's nice. Okay. And then what else do you want to do? You want to scale down row 3? By what? Okay, 1/5 of row 3 back to row 3 gives us -1, 1, -4, 2, 7. Good. No. Oh yeah, that worked out nice. So 1/6 of row 2 back to row 2. Okay. Good. Now what? Row 1, row 3 to row 3. All right, good. Got to pivot. We might get two more. What should we do now? Row 1 plus row 3. I think I'm okay with it. So row 1 plus row 3 would be -3/2. So -1.5 plus 1, right? I think I'm okay. Oh, -7/2 plus 2. Okay, I believe that. Okay. Thank you. All right, good. Good catch. Now what? -3 plus row 3 plus row 1. To where? 1, 0. Oh, 0. 1. -5. Oh, no more fractions. Oh, this is there. Can I also do this? Oh, did that? Anybody notice anything from that? What's next? Right. Row 2 plus row 3, and I think this is probably going to be the only thing we can do. So 1, 0, 0, 1, -5, 0, 1, -4, 3, 2, 0, 0, 0, 0, 0. What now? Can we do any more elimination? No, this is reduced row echelon form. So we now have the means to find a basis for this null space, but let's be careful about how to write down what that is. So this last matrix we got, what does this tell us? I have no idea if this doesn't work. What do these two rows tell us? We know what x1 and x2 are, sort of. We can say them in terms of other things. What's x1 equal to?
5x5 minus.
So minus x4 plus 5x5. And then what's x2? Did you say -4x3? I think all these signs are actually going to flip. Because remember, we essentially got to move these over to the right-hand side of the equal sign. So I believe that's what x1 and x2 are. So x1 and x2 are lead variables. x3, x4, x5, those are all free. So what do I do with my free variables when I write them out like this? What do they become? They become singular parameters. So I'll call them A, B, and C. So if you write these as parameters, I could basically do this. This vector, x1 all the way down through x5 is equal to what? Well, it'll be something in terms of A plus something in terms of B plus something in terms of C. Zero, 4, 1. I think all these have to have 5 entries, right? So let's be careful. So A belongs to X3, right? So what does X1 equal in terms of our parameters? Looks like it's 0A, negative 1x4, 5x5. What's X2 equal? 4x3 minus 3x4 minus 2x5. What's X3 equal? So these next three should be 1, 0, 0, 0, 1, 0, 0, 0, 1. Are we done? So we're gonna just, we've been reducing so long. Let's go back to what the initial question was. What's a basis for this null space? So what is the basis? Should we remind ourselves what the heck a basis is?
Base, these and all that.
The basis is those 3 column vectors. Because what is a basis? Right. So what is the thing in this case that those 3 vectors span? Not all values of A, just the values of A that do certain things. The null space. So we usually write that like this: null A has this basis. So in curly brackets, 0, 4, 1, 0, 0, negative 1, negative 3, 0, 1, 0. And finally, 5, negative 2, 0, 0, 1. So if I take any combination, well, that's the way I want to say this. Oh, I think I was right the first time. If you take any, no, it's not. So the way we got this was AV equals this 0 vector, right? Oh yeah, okay. I was right the first time. I keep doubting myself. Any combination of vectors I make from those 3 right there. So take anything you want from that span, and I multiply it by A, what's going to happen? You get the 0 vector. So that's what the null space is. I found the entire family of vectors that when I multiply A by anything in that span, I get a 0 vector back. How we doing? So again, every matrix will have a null space. Sometimes it only has 1 vector in it, but in this case, it has a basis of 3, any combination of those. How we doing? All right. How about the column space? What did I say the column space was?
Span of all the columns.
Span of all the columns, right? So how do I find that? Is there any chance that all 5 of these vectors are a basis for the column space? I say no. But why is the answer no? What does the basis have to have? Well, like there are two conditions it has to meet. That's for a subspace. So that is true, but basis, like a basis is a a basis is a subspace, but it has like more requirements on from that. So it's linearly independent. As long as you're not too picky about what the span is, we can usually check that one off for free. This will span the column space of A. I can promise you that. Every basis spans something. But is it linearly independent? Why am I saying for sure this is not linearly independent? So that's definitely true. So this is the same matrix as last time, right? So the fact that we got all an entire row of zeros means that essentially one row was identical to another, or essentially identical to another. But also we have 5 columns and 3 rows. You're going to have some dependence there. All right, so one thing that has been pointed out is we already did this. So we've already reduced it. So let's write down that reduced version. Did someone write down their notes so I don't have to keep flipping back? 1, -5. All zeros, okay. And now they want a basis for the column space. And what the column space is going to look like for this matrix, the reduced one, is this, basically C1 times 1, 0, 0 plus C2 times 0, 1, 0, and so on, plus C5 times -5, 2, 0. But here's what's really nice about the fact that we've reduced this matrix. We know that we don't have linear independence, but we know which vectors we can scale back to and still have linear independence. How many of these vectors can I throw out and still keep the same span? Maybe it would help if we look back at our last example here. So we have 5 values of x, right? Which ones are free and which ones are lead variables? Actually, it's just 1 and 2 that are going to be lead. So the lead variables are always going to be dictated by where your pivots are. And in this case, it's only x1 and x2. So in the first row, x4 and x5 depend on x1. Or, sorry, vice versa. So in row 1, basically you can kind of set whatever x4 and x5 are with those parameters, and then x1 will be defined by a consequence of whatever you decide there. In the second row, x3, x4, and x5 are going to dictate what x2 is. But what that also says is that I can basically make whatever combinations I want just by using x1 and x2, because they're going to govern everything else. So because of that, the column space is going to be simply the vectors that are given by those pivots. So I think the notation that Infinity will give you is this: call A is equal to the basis of these 2 vectors. 2, -5, -5. -3, -1, 5. Because that reduction we did shows that basically x3, x4, and x5, you could basically cobble those together based on the first two columns. So the thing I gave you, A, are those 5 columns linearly independent? No, they're not. But are these two here? Yes. So this is a good basis for the column space. How we doing? Questions so far? Questions on how we whittled it down to those 2 vectors and those 2 alone. Does this look familiar at all to you? Does this look like something we've already done? I mean, so the very first thing we talked about today was kind of the heads up I gave you on homework 4.3. This is the way that Infinity wanted the bases for. I think section 4.3 was just about bases, right? And their dimensions. Finding a basis for a column space of a matrix and finding the basis for a matrix on its own, those are typically identical things. Because the way we think about matrices is, or the span of the vectors in a matrix is the combinations of this column and this column and this column and so on. So by default, in a lot of applications, we're always looking at column spaces. We always want to know what the columns of a matrix will span. How are we doing? All right. What about the row space? What's the row space tell us? Span of the rows, right? So in the past, or in the last example, we were looking at the span of 5 columns. Now we're looking at the span of 3 rows, right? So basically what I'm looking at is all the linear combinations that look like this. -2, -3, 12, -7, -16 times C1. So far I'm taking these column vectors or these row vector, or not row vectors, rows of a matrix, and reinterpreting them as columns. So kind of inherently in doing that, what am I doing to this matrix? Remember that operation is called when you turn the columns into rows? Right, what I'm kind of looking at is A transpose. And if I transpose it, I'm no longer looking at the row space of A. What am I really looking at? I'm looking for the column space, CLO. What am I doing? COL of A transpose. Do we know how to find the column space of a matrix? I just saw you do it. So I believe wholeheartedly you could reduce this by hand. Do I trust you to reduce it using a calculator? I hope so. So I'm gonna write down whatever numbers you tell me. Unless you want to see MATLAB again. Okay. That's the reaction I'm used to. I pulled that out from my differential equations class last week, and you would have thought that I just threw cockroaches on them.
1, 0, 0.
That's good.
0, 1, 0.
Oh. Uh-huh.
2, 4, 0.
This is reduced?
1, 3, 0.
That doesn't sound right.
-5, 2.
If you ask this to reduce row echelon, that should not have anything else in that left column.
1, 0, 0, 0, 1, 0, 0, 0, 1. Restaurant.
Did anyone else get that as well? So there are two commands in that matrix menu. There's ref and there's ref. This reduced row echelon form, ref, will give you it'll give you the like stair step upper triangular form. Reduced row echelon will, any column that has a pivot, everything else will be a 0 there. So the only columns that have entries that aren't exactly 1 will be free variables. But someone said they got this thing reduced down to the identity and then, or at least what looks like the 3-dimensional identity and then these last 2 rows. Was that what I was hearing? Sorry, everyone, I feel like I got to do this. Really? I mean, does it tell you what the error is? Are you trying to invert it? It's just do it. Did you transpose it first? I don't suppose anyone knows the command. Oh, what did you get mad at before? How to transpose. Okay, now I've seen the third thing now. I'm confused on why you're. Okay, so in your calculator, TI calculator, are you transposing it first?
I think you're supposed to do the RREF and put in your A, but it's for the transpose. There is like a transpose.
Yeah, I think if I do RREFA, this is bad. No. Yeah, so we've seen that one, right? But if I do RREFA, that like that. Yeah, I mean, I wonder what the calculator thinks you're doing.
Wait, put it in, put 20 or -1? It should be -1.
I got -20. But I didn't write down -20 on my slide. Oh, that's okay. I screwed it up and then I all right, I got 211, so I'm not gonna hold you up any longer. Oh, let's debug it tomorrow. I'm almost sure this has a simple solution that we're all overlooking.